All right. Hello, everyone. Thank you for joining the webinar today. My name is Russell Hoppenstein. I'm an RF system engineer at Texas Instruments. I work in a system engineering marketing role where we're focused on the aerospace and defense market segment and supporting solutions across all the TI portfolio to support your needs. Today, I'll be talking about improving our SWaP-C for space-grade phased array systems. And I will try to leave some time at the end of this presentation so that we can address any questions that come up. So in your webinar view, you should see something that has like a Q&A box. So feel free when things pop into your brain, go ahead and type in a question. I won't address them right then, but at the end, we'll go through any of the questions that are in that chat session. All right, with that, I think we'll go ahead and get started. So first, we're just going to look at the basic implementation of the phased array system to kind of just try to level set a little bit so we're all talking the same language to some degree. Now, if we look at the operational frequencies that we're dealing with, now certainly the stuff that's in the L, S, and C bands, this is stuff that's covering basically up to 6 gigahertz. These have traditional, conventional architectures associated with them that can cover up to those bands directly. If we push that out all the way up into X band, now we have some RF sampling architectures that now can support all that low frequency stuff, the mid frequencies, and then go all the way up to 12 gigahertz. As we start to push higher into the K bands and beyond, now we need to do something a little bit different. RF sampling is not hitting these things directly at this point, so adding some kind of a external up and down conversion in order to hit these higher frequencies is the approach that we'll typically use. Now, the system solution here is ultimately going to be dictated by the laws of physics. We're talking about a space solution. If we're going to put something up into space, we really have to make sure that this is going to be a relatively small and compact solution. So to make that happen, we need to have small antennas. We need our satellites to be relatively small. That's going to in turn dictate wavelengths that are going to be short. Short wavelengths correspond to high frequencies. And if we're dealing with high frequencies, we have to have the impairment of the propagation. We don't, the higher frequencies don't propagate quite as well as the lower frequencies. So that presents some challenges in and of itself. Certainly as we start pushing into the high frequencies, we'll see a lot of this in the Ku, K, and Ka bands. 18 to 30 gigahertz is kind of typical for these frequencies. And we're going to be pushing into large phased array systems in order to mitigate some of the propagation losses and power requirements that we would need when we're dealing with these high frequencies. Okay, so we're just looking at a single antenna element. This is a picture of a microstrip patch antenna, just as an example. It doesn't have to be that. There's lots of different options here. We can talk about dipoles or printed dipoles, the microstrip patch, waveguide apertures, or it could be a physical dipole or a horn. Doesn't really matter. The shapes will all be slightly different. But generally speaking, a single element's going to be fairly broadband, not very directive. So it's not going to be very discerning as far as the location in which the energy is pointed. And of course, it's also not going to be a high gain type solution there. So in order to try to really push a lot of data into a system like that, you'd have to be driving lots and lots of power because your antenna doesn't have very much gain in and of itself. So basically, it's poor directivity, the energy density per unit area is low, and you don't really have any adjustment capabilities to move your signal around to where the users are, or alternatively, not look in places where there might be interference and jammers. So we can introduce the antenna array theory. This is a case where we have not just one element, but an array of elements. Basically, you can think of this initially as just a linear array of elements. The combination of all those kind of tends to sharpen the pattern. Another way of saying that is just saying it's got a higher directivity with that antenna pattern. So if we're improving the antenna gain, we get a higher energy concentration per unit area with this type of a system, and we can scale it, right? More elements in our array translates to a sharper beam. Now, why would we bother with all this extra complexity and having more elements and more channels and such? So the main reason here is we want to mitigate a lot of the lossy atmospheric effects that are happening during propagation. So if we can go to a higher array with more directivity, it gives us a higher gain antenna that we can push more signal down into the ground. And ultimately, this also requires less power per element. We're getting the summing effect effectively of this array. So the PA requirements, the power amplifier requirements per channel is relaxed a little bit. And that's very helpful in cases when we're dealing with very high frequencies. It's hard to get super high power, high efficient amplifiers that are operating in the K-band and beyond. Now we can expand this linear array into a planar array. So now we have a two-dimensional structure here. So we have elements in both directions. This particular picture here is just showcasing something that looks like a 4x4, 16 elements, a planar array. And now we can focus the beam in both of our physical directions. And we'll start talking about how we can manipulate the direction of that beam by adjusting the phase of the corresponding elements. And that way we can adjust it. We'll look at that here in just a second. But these phased array systems, they vary somewhat widely. They can be a case where we're talking about just a few elements, but in some cases we're talking about hundreds, maybe even thousands of elements in order to get the gain and the power transfer that's necessary for these systems. So the higher number of elements, the higher the directivity, more gain, and the sharper the pattern. So the theory here is with these linear arrays is that we can introduce a phase shift per element to electronically steer the beam. So we're not mechanically having to move the antenna structure to move where the direction of that beam is in place. So we've gotten rid of all the sort of the mechanical motors and things like that that might have been in older systems. But now we're achieving that same function by just adjusting the phase, relative phase, between all the different elements in that array. So essentially, the beam is going to be steered into the theta direction where all of the wave fronts are coherent. So by adjusting that phase, we can get to a point where all of these phase fronts are now coherent, let's say in this plane, and that way the beam is pointed in this direction. This is a very powerful tool in our phased array systems so that we can really fine-tune what we want. And we'll call this a beam-forming array now. So the ability here to move that beam around has now introduced another level of complexity and another level of functionality to these systems. All right, so let's look at some of the beam-forming systems. So we'll start off just looking at the analog beam-forming solution. So this type of an approach, it'll use the standard, what I call the standard transceiver block, however that is going to be defined for your particular system. But basically one transceiver to get you up into the RF realm, And then from there, every element will have its own kind of independent gain and phase adjustment capabilities. So 16 element array as an example, you'll have 16 independent gain and phase adjustments in each of these cases. So this certainly works, but now we get to the case where calibration gets to be a little tricky. Maintaining your accuracy gets to be a little tricky. You got a lot of analog components in here that have to be adjusted. Things are going to shift a little bit by temperature. Different devices are going to have slightly different transfer functions and the like. So getting this to maintain across, a wide bandwidth, over temperature, over different use cases, that's going to be a tricky endeavor. So we'll shift maybe to the next form here, looking at kind of a hybrid beamforming approach. So this is a combination where we can still have that sort of traditional digital RF transceiver, but we will have each one of those transceivers will sum out or split out into multiple analog, let's say, front ends that have their independent amplitude and phase adjustment capabilities. And different systems do things differently. This could be anywhere from 2, 4, 8 different elements. So this, again, has the analog gain and phase adjustment capabilities in these cases. But it's not the entire array, because we still have multiple transceivers that are working with each of these analog front ends. And so we have some adjustment capabilities kind of in the digital domain here, and then some fine-tuning at the smaller element level in the back end. I guess I should say the front end here. So it still has some of the same calibration and analog accuracy implementations, but you have a little bit more flexibility because you can adjust some of that here in our digital transceivers. And then we'll shift to kind of the holy grail of these types of systems, which is a full digital beamforming application. In this case, every antenna element will have its own digital RF transceiver associated with it. So this is very powerful. Now we've eliminated the analog gain and phase adjustments at the antenna level. We're pulling that back into the digital domain in our digital RF transceiver. This gives us much more precision, much more flexibility in adjusting these gains and phases across all the different elements of the array. With that precise control, I'll show that we have a lot more flexibility in moving beams around, multiple beams around, moving where nulls are going to be located to help in that situation. So this is really a nice system. We can utilize the RF sampling architectures for this feature to handle not only the conversion up to RF, but the gain and phase adjustment capabilities. But we do have to be wary because this is a very computationally extensive application. We've got lots of digital processing that has to go on here to manipulate these signals. And there's a large digital power dissipation since you're multiplying lots of different transceivers here. So we'll have to keep those limitations and concerns in check appropriately. All right, so the digital beamforming here. We got multiple beams. We can move these things in independent directions, and we can even potentially adjust directivity of individual patterns. There's lots of different flexibility here. So the more flexible we are, the more computational extensive these systems are going to be. So that's part of the trade-off in these types of systems. But we can create multiple and steerable beams. We can move and track multiple targets or users simultaneously. And we can also mitigate jammer and interference with this type of system. So let's just think about that for a second. Multiple beams, we can have the case where there's, multiple users or multiple targets at different locations that can be independently tracked. As these targets move, this beam can also move accordingly in order to keep that tracked. And if these other users or targets are not moving, these beams could stay static potentially, so that you've got independent control to move with your moving targets, keep static your static targets, or any combination thereof. The other angle is you can also think about this as not only steering the beam, but also steering your null patterns. So if you have a case where you've got a null in this location, there could be something here that is jamming. And if this thing is jamming and it's hitting you kind of in this physical location, but you don't have a beam that's basically sitting there, then the effect of that jammer is not going to hurt you too bad. So basically, in summary, is we can move these things around to cover different users. We can also move around the nulls so that we can mitigate any interference or jammers in our system. All right, there's a myriad of different phased array radar challenges with these solutions. So we're talking about something that has a high number of elements. So high number of elements, we need to be looking for cases where there's high levels of integration. We need flexibility, so we can adjust frequency quickly. We can adjust gain and phase quickly. We want to be able to adapt to jammers and interference. We want to be able to support higher bandwidth and more complex modulation schemes with higher peak to average ratios. So we need solutions that have better linearity performance. And we're talking about a transmission scheme that can support very high bandwidth, instantaneous bandwidth signals. So all of these areas kind of fall under the signal chain solution. So we're looking for solutions here, new devices that are coming into the market that can support these types of applications with flexibility, bandwidth, and the transmission. Phase noise. All of these devices, when we're talking about data converters or LO sources, we're going to be very concerned about phase noise performance. So we're looking for solutions here that have very low phase noise for our clock and our synthesizers for our LOs, low residual noise as well. So we're looking for new and better clock solutions that can satisfy those requirements. Now, with more integration, more channels, power consumption, power dissipation, this all translates to thermal, getting rid of the heat in your chassis. So we got to look for more efficient power solutions, optimization there from a physical size, more efficient in order to make these systems work. And since we're talking about lots of different channels in our phased array system, we need to make sure all those different channels are kind of talking to each other nicely. They're all synchronized well together. So we need some system solutions here that can make sure that all of the data converters, all the RF channels are all going to be properly synchronized so that they can maintain the proper phase and gain alignment to make the array work as it's supposed to. And then, of course, signal processing. As we talked about, the signal processing becomes increasingly more challenging as we get to these, more complex digital beamforming systems. So let's look a little bit at some of the architecture trends. What do we know? Well, we know there's going to be lots of elements, and lots of elements is going to translate to lots of channels. and there's going to be lots of channels, and we're still kind of a physically small structure, relatively speaking, so lots of channels are going to be crammed into a close proximity. So now we'll look at the SWaP-C argument here. So the SWaP-C, size, weight, and power. We can't discount the cost angle too, of course, as we can kind of improve on a lot of these other areas. A lot of times that's going to translate to a cost improvement as well. So certainly on the size front, we're looking for solutions that have more integration, more channels crammed into the same device, and certainly optimized power solutions or optimized, better power consumption type devices, lower power devices. We're trying to cram more stuff into a physically smaller space. You can only get so much heat out of a chassis, so we're looking for more efficient solutions in that area. On the weight front, as I'll show in a little bit, as we're moving to plastic type packages as opposed to the historic conventional ceramic type packages. So this is one area that we're going to be saving certainly weight, also physical size with that transition. And then on the power front, as I mentioned slightly before, optimizing the integration, optimizing the power solution. So this is not only the devices themselves, right? We want the devices themselves, let's say the devices in the RF signal chain, to be lower power and more efficient. We also need the actual power solution that's powering up all this stuff. We want that to be a more efficient, physically smaller, looking for ways where we can have one power solution that can power up multiple chains of devices so that we don't have to propagate so many different devices in one given system. So we'll introduce the RF sampling architecture. Okay, so in the RF sampling architecture, we're coming in here from digital baseband, coming, let's say, out of the FPGA front, and we're converting directly up into the RF space. So not the conventional architecture with a analog baseband, converted with analog mixers. This is all happening with digital up and down converters inside these components, and then a high-speed DAC or ADC that is capable of outputting in the RF band directly. And there's two different kinds of flavors that TI offers up. So one of them is the integrated transceiver. So the integrated transceiver part that we have released right now is the AFE 7950. This one will come in space grade solutions. This is an integrated solution that's a 4 transmitter, 6 receiver, all integrated into one package. This one will support up to X-band frequencies. As an alternative, we can look at discrete converters. So for example, TI's DAC 39RF10 and our ADC 12 DJ5200, so our corresponding DAC and ADC. These are also available in space grades. This is a 2-channel for each of these, essentially. These can support very wide bandwidth applications. So there's some different, design choices here, whether you need or require very wide bandwidth cases or more towards a highly integrated solution, more channels crammed into the same space, same part. And then, of course, on the clocking solution, we've got a couple of options, an LMK 04832. This is a clock jitter cleaner that also is a clock distribution chip that can support all of the clock needs that'll support the lower frequency clock needs, FPGA clocks, sysref frequencies for the JESD 204B protocol. It can support reference frequencies for higher frequency RF synthesizers. So a myriad of different clock outputs, all with different divide outputs and things like that. And then for the high frequency sampling that's needed for the data converter itself, or if there's an up converter for an LO, we'll look at the LMX2694 and the LMX2615. These are space grade solutions that are high frequency RF synthesizers that can support the low phase noise requirement needed for those opportunities. So let's look how a system like this might be put together. So I'm showing you a block diagram of a 64T, 64R planar phased array system. And if we look at just one of these elements, this is an example using TI's AFE 7950 device. So again, it supports 4 channels. So we've got 4 antenna elements associated with it. So we have a little 4T, 4R block in this location. We can take multiple copies of that solution. We can put those together with a single FPGA approach. And so now we've got a tile. We've got effectively a 16T, 16R tile, 1 FPGA, 4 AFE parts, 16 antennas. And with this tile, we can optimize certainly the clocking, certainly the power solutions, have 1 power solution that can support FPGA and all these RF sampling transceivers as well in 1 solution. Okay, so now we got a 16T, 16R tile. How big is your system going to be? Well, we can cascade these tiles appropriately. So if you need to build a 64T, 64R, we'll propagate 4 of those larger tiles, but this is very scalable. We can go up to much higher systems as needed with just the propagation of the same kind of tile structure. Very flexible type solution. I want to introduce, the superhead. This is not what I call the conventional superhead architecture. The conventional superhead architecture would maybe up convert to some relatively low IF frequency, maybe a few hundred megahertz, and then you would mix up to the RF realm. That's not exactly what we're doing here. We're just kind of scaling this up or pushing this up to higher frequencies. We're still using the RF sampling architecture, with this block. So going, effectively straight from digital baseband up to RF frequencies here. So it's RF frequencies, but for this purpose, we'll call it the IF. But the IF may be something like in the gigahertz, 8 gigahertz range, something like that. So there's definitely some advantages here with using these high frequency RF sampling devices in this type of a superhead, because if we can push this IF frequency to higher frequencies, it gives us a couple of advantages. One is when we do the subsequent mixing stage, let's say to get up into, into K bands here, we can get a decent amount of separation between our images that are caused by the mixer function here. So that way it makes the filtering a little bit easier. As they'll be far enough away, we can have some pretty benign filtering in order to make that work. The other advantage with going with a very high IF frequency is it relaxes the frequency requirement for our LO source. And so now this doesn't have to be quite as high frequency as it might otherwise be. And that gives us some more flexibility in using some parts that are, pushing up into the 15 to 20 gigahertz range to still be applicable for K-band frequencies, up to 28 or maybe 30 gigahertz. So once we've converted up into K-band, adding the appropriate filtering and power amplifiers, LNAs for that approach, now we have a very nice performing K-band solution using our RF sampling architecture plus an up-converting, down-converting mixer. So let's look a little bit at some of the quality standards. And I don't expect you to be able to read this slide. I'm going to focus specifically on a couple of different angles here that I highlight here. And then I'll show this a little bit more detailed in the next slide. So this is the quality standard breakdown. We're specifically here talking about for space. So I'm going to start on this side of the table looking at the QMLV standard. This is a kind of an industry standard. It's a space ceramic solution. This is what traditional space grade solutions have always kind of been. They're like, oh yeah, we need these big ceramic based devices in order to handle the radiation. And that's certainly what they're geared up to do. They're supporting deep space and geosynchronous orbit type satellite solutions. Every device is going to be a little bit different, but we're talking about something that's, generally speaking, in the 50 to 300 KRAD. Most of these type of devices are probably going to be around 100 KRAD or so. That's kind of where they typically land. These are perfectly good devices, suitable for these applications. But there has been a shift and a trend in this market space as the space applications have grown. It's just like, yeah, the ceramics are big, the ceramics are heavy, they're physically big, which means when you're trying to deal high frequency and things for RF purposes, we don't like big. We like small and tight and concise. And all the parasitics associated with a big, physical package tends to hurt things as we start pushing into the higher frequencies. And as we mentioned, we're trying to do that more and more with these systems. So we'll introduce a TI quality standard, which we're calling the QMLP, the P for plastic. So essentially, it's almost all the same qualification standards as the QMLV, but now we are putting that into plastic packaging. We're still adhering to basically the same radiation standards, 50 to 300 KRAD, 100 KRAD typical. It's still applying to the same geosynchronous orbits and deep space applications. It's just now we're physically smaller, we're physically lighter. We can now adhere to some of the higher frequency PCB designs that we're familiar with for industrial applications. We can now shift those very quickly into space grade applications. And then another standard that we call the Space EP. So the Space EPs is space grade, that is space enhanced plastic. So still in plastic packaging, but these have slightly reduced radiation standards. These are typically used for LEO applications, low Earth orbit applications, where the radiation requirements, the radiation tolerant requirements are not quite as severe as when we go up into the geo or deep space type applications. So these devices are going to typically be in the 30 to 50 KRAD area. Again, they're small, they're light, they're in the plastic packaging. We can keep the designs very small and concise. We can reuse some of the PCB design resources that we've used for industrial purposes with these types of devices. And from a cost perspective, if you don't need the high radiation standards and you're only doing a LEO type project, we can save you some money, relatively speaking, compared to these flavors, so we can get a lower cost solution. So we're finding lots of new applications for the Space EP side of things. You'll see this when we talk about, if you see part numbers that TI puts forward, we'll usually put a dash SEP on the end to indicate that that is a space enhanced plastic type device. Okay, so next I want to showcase to you some of the reference designs that we have already released. You can go on to ti.com and view anything that I'm about to show here just to get more information. We'll have user's guide. There will be some test data associated with it. There'll be design files. So if you like what you see and you're like, oh, I'd like to copy some of that or a portion of that, you can get access to the design files, the bill of materials, all that kind of stuff that can help you as a starting point, at least, for some of your designs as well. So the first one I'm going to talk about is a TIDA 010274 reference design. This is a RF sampling transceiver. It is designed so that it can support not only industrial applications, but also the space-enhanced plastic we just mentioned and a full space-grade solution as well. It's configured as a 2-transmitter, 2-receiver part. This reference design's claim to fame is that it supports a very wide instantaneous bandwidth. So we can support 5 gigahertz of instantaneous bandwidth with this solution. Analog bandwidth will go up to X-band frequencies. And we've incorporated basically everything to be a complete solution on this reference design. So we have RF active balance for handling the single-ended to differential interface to the ADC, and the differential to single-ended interface for the DAC for transmission. We've got clocking solutions on board that will support the clocking of each of those respective DACs and ADCs. We're clocking the DAC at 10 gigahertz. We're clocking the ADC at 5 gigahertz. Correspondingly, both devices are actually sampling at 10 gigasamples per second. So the ADC device, for example, is using a dual edge sampling approach in order to effectively double, the sample rates double what the clock rate is. Also including power management solutions for high efficiency, low noise options. And we'll focus here on, certainly satellite comm payloads, radar systems, electronic warfare, anything that needs a wide bandwidth type application. This is a picture of the board, and we've got the ADC device located there, the DAC device located now on the bottom right, incorporating the clocking device and the LMX2694, and the LMK04832. So again, this one's providing all the low frequency clocks and distributions needed for the FPGA and the sysrest for the JESD IP, and the LMX high frequency synthesizer provides the clocks to both the DAC and the ADC. And then we got these little bitty RF amplifiers. This is the active balun parts. They're really small, which is good because we can pepper them in where they need to go. Since we're talking about some of these large phased array systems, lots and lots of channels, we don't want to, have lots and lots of these big parts here. We want these to be nice, small, compact. We can get them really close to the pins of the device so that if we have very high integration, lots of channels, we can pepper those in as necessary. The power bore, as I mentioned, this is a space-enhanced plastic design. So a combination of DC to DC converters and low noise LDO devices to support all the different voltage rails that are required for this particular design. So this is a key angle when we're talking about these RF transceiver systems, is we got to be cognizant of the power supply. We don't want noise that's coming in from the power supply side of things to infect the analog performance. So we've taken a lot of care in not only designing with the proper parts that are low noise, but the proper layout as well, so that we don't have switching supply spurs, from one switcher infecting a sensitive analog rail that might end up getting into a converter and then causing some problems. So this is one of the advantages of the reference design, is that you can kind of see and get a glance on the way that we've done some of the layout work and keeping LDO outputs separated from switcher outputs and things like that in order to minimize noise and spurious from those solutions. And if you have a full space gray need, we've got a solution for that in place as well. This is a nice thing that the TI portfolio has, is we've got a nice portfolio of full space grade and SEP grade space power devices, DC to DC converters, inverters, LDOs, things like that. So pretty much we can put together any kind of a system that you need from a power perspective in your space applications. This design utilizes a daughter card approach. So the power card, for example, is a daughter card that plugs into the back side of the board here. This facilitates using basically one design for the high-speed data converters, and I can pop off the space grade, the space enhanced plastic grade. I can pop on the full space grade power solution. If I want to compare that to the industrial power solution, I can do that. Without having to change the data converter board, I can try out different power solutions and debug any problems and things like that. So this has been a nice approach for being able to look at the combination and comparison of all these different power solutions. We've also do a similar approach for the clocking on the top side of the board, so we can try different grades of clocking devices between the space grades, the industrial grades, and the full space grades and space enhanced plastic, and look and compare the performance of all those different combinations. Next, we'll look at a different reference design. This is the TIDA 010260. This one now is using our AFE 7950. This is the integrated transceiver device. The device here is supported as a 4T6R. This particular reference design is configured as a 4T5R. So one of the receive channels is not used. It's in a very small form factor. This is a VITA57 form factor. So if you're familiar with that, you'll know how small it is. And we got a lot of stuff crammed in onto a very small space. This particular design is configured where we can use different channels for different purposes. So we can configure a couple of the channels operating in X-band for communication purposes. We can allocate a couple of the channels for S-band. And then we use one channel that's actually operating in L-band for GPS receive applications. So this design not only has all TI parts that are space grade, it also has all the passive designs defined or identified to be space grade passive components. And when I started this design, I didn't think that was going to be that big of a deal, but I'm kind of finding out that space grade passives are not quite as easy as you might think. There's limitations in capacitor physical size, values, so it certainly makes it challenging for high-speed work where you're trying to get very low capacitor values, and then for bypassing purposes, very high capacitive values. And then certainly the inductors for a lot of the DC switching power inductors, this is a tricky area as well that I found out with this reference design. So I'll show you another picture of the design here. This is the real picture of the device. So we've got the AFE device sitting in the middle, LMK clocking device in this corner, the RF synthesizer device in this corner, and then smattered around the periphery here is the power solution that makes everything go. As I mentioned, this is a VITA57 compliant board, so there's some height restrictions on the back side of this board, so almost everything had to be on the top side, which made the layout here a little bit more challenging as well. And then, as I mentioned, the flexibility with this solution to be able to allocate channels for different purposes all in the same design is very critical. This is the reference design of the board, talking about the LMK, the LMX synthesizer, all the power into the AFE 7950, and then all of the active balun interfaces utilized here. So we don't have to have any passive baluns for most of these channels. Again, this helps facilitate making a really small, compact design. And then the power solution using SEP flavored DC to DCs and LDOs. This is another example where we wanted to be very efficient in its physical size and just overall efficiencies. So pretty much using DC to DC converters, almost all the analog rails, with the exception of the most sensitive ones. Another reference design is the TIDA 010259. This is from clocking. I saw a mention in the chat about synchronization and clocking. I'll talk more about that when I conclude, but this is an area that's a very nice solution for distributing your clocking for very large phased array systems. If you remember, I talked about all those different tiles, and as we cascade lots of different tiles, well, each one of those data converters is going to need a clock source to go along with it, and this is a great way to distribute that clock source across lots and lots of different data converters, lots of different elements and channels or tiles. So this is an LMX 1204 and its family. We are demonstrating how we can cascade these devices together in order to achieve higher distribution outputs. So a normal 1204 is a 1 in, 4 out, but we can cascade these together with an additional 4 elements. So now we get a 1 in and a 16 out on the back end. And it's not only the clock that we're providing, we're also providing the sysref signal. So there's 4 copies of the clock and 4 copies of the sysref. So if we're talking about clocking JESD compliant data converters that are going to need sysrefs as well as their sample clock, with this device we can do both of those with one function. There's also some synchronization features that are built in to this device where we can do some sysref windowing and adjust the programmable delay in order to get things well synchronized across multiple channels. We've got about a 2.5 picosecond step delay adjustment even at our highest frequency. And I'll show you the performance here that's very impressive. So this is comparing the 2x channels or the cascaded LMX 1204, so basically 2 layers of the LMX 1204. And I'm comparing that to basically the best signal generator piece of test equipment that I can get my hands on, which is the Rohde and Schwarz SMA 100B. So comparing that, really no noticeable degradation out to about a megahertz offset between those 2 approaches. And then if we look past that, we do see some thermal noise impact, but it's pretty minimal out here. So we can cascade up 2 layers, 3 layers, 4 layers, depending on how many clock sources your phased array system ultimately needs. So the 1204 device, this is a family of parts. We've got flavors that don't include the sysref solution, so if you don't need that, you can get ones without it. A new device that includes some buffered output delay features. That's kind of nice too if you need an additional layer of control for synchronization purposes. And then specifically for your space grade solutions, SEP flavors and full space grade flavors of doing the same thing, operating out to 15 gigahertz. And this reference design is an FPGA, Versal-based FPGA, rad hard kit. Lots of parts on here. I'm not going to go through all of these. I'm just going to flash some of this stuff up. We've got the Versal FPGA device. some of the DDR termination power devices here for supporting that. More power solutions and microprocessor solutions, controllers, interface type parts and LVDS drivers and receivers, translators, and certainly same part that we've seen before, the LMK04832 for generating a lot of clock distribution solutions. So if you want to get access to some and all of this information, the best way to go is to get onto TI.com. You can get to a lot of this information in a couple of different ways. One way is you can just simply type space into your search bar. That'll bring up a whole list of stuff. And if you come down here and you'll see something that says Space Design Resources, and you can click on that. That'll get you to a good place that you want to go. The other alternative is you can type in aerospace and defense, and that'll get you to a landing page. And from there, you can select space. You can also select other defense-related things as well. And that'll get you to the landing page that I'll show you here in a second. Okay, so that'll get you to the space landing page. This is where we're going to house lots of information that is specifically tuned towards these applications. So we'll get access to some of the latest devices that have just been released. You can see access to information related to our quality standards. We're going to put application notes here. We're going to put, obviously, new products. Some of the reference designs that I've showcased today will be there. Any other technical papers, documents, white papers, things like that. Product guides, webinars like we're seeing today, and space news. So anyways, anything and all reference information that is kind of related to this space, we want to put it here, kind of make a convenient place for you to access without having to remember lots of different part numbers and lots of different URLs and things like that. And certainly if you get to the point where you're looking for purchasing parts, we've tried to make that easy as well, going on TI.com and the TI eStore. So we have lots of information here for being able to quickly download information, documentation, being able to select parts. Certainly want to conveniently buy. You can do that through the TI.com and through our eStore. Certainly if you're talking about a higher volume opportunities, I encourage you to reach out to your appropriate salespeople, and then we can put together, customized solutions for whatever it is that you need. Okay, so that kind of concludes this portion. I will now look at some of the questions. And I see a few of these have come through the chat, so I'm going to address those. Give me 1 second here so I can see what I got. Okay, so one question came in that says, are you going to talk about synchronizing all of those tiles? And that is an excellent question, because that is one of the key tricks of the trade, so to speak. So let me get back to that picture. So we have this case where we have lots of these different elements. And I'm not showing it in this particular block diagram, but each one of these red parts, that's an RF sampling transceiver. It's going to have a clocking solution that goes along with it. And yes, we need to synchronize these devices together. So this is an area that we do spend a lot of time and work and effort on in being able to demonstrate synchronization across different elements, and we have some nice parts in our clocking portfolio that can help facilitate that. So, for example, if you recall, I talked about that clock distribution chip that has some features that not only can we synchronize the dividers, like on our RF synthesizer parts, so if we have multiple synthesizers that are employing dividers, we can synchronize those outputs to make sure those are deterministic and in phase. We can adjust sysref windowing using some of our newer clocking devices, so that if there's some sort of a delay there and we need to shift or delay to get within the sample and hold window of the high-speed data converters, we have the opportunity to detect that and to adjust that sysref in order to get things properly aligned. And then moving forward with a part like our LMX 1205, where we're introducing additional delay adjustment capabilities so that if our sample clocks need to be aligned better, and we typically see this in cases where maybe you have cabling that's going to all these individual devices or these individual tiles, and they're physically separated. Temperature effects, things like that, might adjust the phase at different times and different points in its use. So having that flexibility to be able to independently adjust the delay on each of those clock elements to kind of calibrate that out can really do wonders in order to keep our device perfectly synchronized in all cases. So yeah, these are areas that we are paying a lot of attention to in order to synchronize across multiple devices using our clocking solutions. There is another question, it looks like it came through, about whether we get a copy of the slide deck. Yes, I think that is definitely possible. So we will make sure that's available to everyone here. I did also get a question before the meeting started related to what are the PCB materials used in space applications for high-speed digital boards. So I'm not exactly an expert in this arena, but I can tell you that the PCB boards that we're using are typically Megtron 6. This is for the high-speed RF type, data converters and the like. So Megtron 6, even for industrial applications, it's a good material, relatively low cost, fairly well available. It's a low loss RF. Can support the high frequencies for RF with low loss, but it also has the added advantage that it's also good for space applications. So that's been our go-to part, certainly for the analog RF boards. And in some cases, we're looking at that for even the digital boards, because we're talking about SerDes speeds that are pushing 28 gigabits per second, maybe even up to 50, 56 gigabits per second. So for the high-speed stuff, it's good for, even though they're, SerDes lines, they're still good for propagation on that front as well. All right, and I see another question that came in. I'm going to paraphrase this one a little bit, but with the increasing demand for high-speed radar and communications in space, what are the most promising advancements in semiconductor technology that can enhance performance for our SWaP-C? So I'll tell you on that front, this is obviously an area that TI is heavily invested in. So we're looking at that in a couple of different fronts. We're looking at that certainly in process technologies that can get more and more integration. We're going to, 28 nanometers down to 16 nanometers and even beyond in order to try to reduce the digital physical size. We can cram more digital stuff in the same space. But in conjunction to that, we're doing some design tricks that are particularly useful for operation into space. Quality assurances, reliability, redundancy within the design to make sure there's not a single point of failure on any one kind of sub-circuit or device in order to make it more robust for space applications. So even though we're looking at stuff that may be in a space plastic package that looks very similar to the industrial versions, there is some stuff behind the scenes that are being particularly looked at so that they become more robust solutions for the space grade applications. All right, with that, I want to thank you all for your attention and appreciate you coming to this webinar today. If you have any other questions, certainly reach out and we'll be happy to help you. Reach out to your salespeople. That's what we're here for. so we can support you in any and all of your needs. All right. Thank you all very much.